Hello, my name's Gary Brown from AIE Global. Today I'll be talking about near-infrared spectroscopy, which is continuing on from my previous discussion. This is being part 3. So here's an example of cheese, particular type of cheese, comes out of Europe. This has become more important in certain, especially in agricultural products, where there are certain advantages a product has because of its origin of where it's been made. So the Swiss, for instance, here's an example of Finnish cheese. You can see the bottom lower left-hand corner. They may have a premium on this particular brand of Finnish cheese because the cows in the pasture is unique and it produces a certain flavour or a certain quality of cheese. Now there's a lot of and they'll try and sell their Finnish cheese at a premium, but someone else comes along from Switzerland and says, well, this is the same brand of cheese and we'll sell this Finnish cheese. And this is a big issue in Europe for country of origin determination. So with principal component analysis, you can see here you go some way to determine, or you could easily determine Finnish cheese from any of the other European brand cheese using near-infrared spectroscopy and just using a qualitative analysis. Now, the other method is we use model development is supervised. Now, with supervised, we have to measure the actual constituent or the value of the constituent we're interested in. So, for instance, I'll talk again about protein in wheat or the total soluble solids in orange juice. We actually have to measure it. So we measure the Brix value. We'll get values for each sample. We measure between 10 and 20 Brix. And then we apply that to the partial least squared regression to determine a result. So in the future, when we use our model to predict the results from new samples, then we will be actually predicting what the total soluble solids are for that sample. And it also can be determined to determine what samples don't belong to the model. So you can determine outliers. So if, for instance, the material considerably changes, then you can also easily determine that as well. And it's also often very important to do that because you also need to know how well your sample is fitting to your model to be sort of have some confidence level that you're predicting accurately as well. So we have a few different measures, a few different ways of measuring the outliers in real time as well. So just going back to the model here, you can see the system onto the right. We need to, with quantitative analysis, we need to be able to do a validation. So that validation graph on the right gives us an indication of how well our prediction is performing. And here's a few examples of models in prediction. So the top one is water soluble nitrogen in cheese, which is measured using Fourier analysis, Fourier transform analysis spectrometer. And here's a good indication. There's an R squared of 0.91, whereas compared to measuring the same sample, measuring the non-protein nitrogen gives you quite a bit. The results drop off considerably, so you only get an R squared of 0.77. So be very confident that we can very easily measure very accurately the water-soluble nitrogen, but you'd be a little bit suspicious of how well you're predicting the protein nitrogen or the non-protein nitrogen because of the drop-off in R squared. So I mentioned previously that the first part of the principal component analysis is or PLS as well, is that we need to reduce the components of the variables down to a manageable set of variables. And here's a simple example of how that can be done. So, or what it would look like in that we've got two variables, and just by realigning the principal components, you can see that principal component 1 on the bottom graph after mean centering is a lot more sensitive to the variation in the sample set. So we're now PC1, principal component 1 is now aligned with the greatest amount of variation in the sample set, and PC2 being orthogonal to, which has to be orthogonal to PC1, will indicate the next amount of variation in the data set. But there obviously hasn't been much reduction here. We've started off with 2 variables, and we've still got two variables, 2 axes. So we haven't done a reduction. We haven't reduced our number of variables, but we have ordered them in order of variation. So here's another example in 3 axes. So here, if all these samples were in one plane, for instance, then we could go from 3 variables down to 2 principal components. Once again, it does show that the principal component 1 is now showing the predominant amount of variation in the sample set. Now, in quantitative analysis, we need to define our results so we know how well the system's performing, and that's done through one of the measures is the root mean square error of prediction. So it's just an RMS measure of the error effectively, but it's done in cross validation, which means you develop a model, you put it on your instrument, you run a new set of samples, and you measure the samples again. So the samples weren't a subset of the original data. So that's a true RMSECV. You need to be a little bit careful, and you see a lot of quoted RMSECVs, which actually are still part of the original subset of data. So they'll take 100 samples of an object, they'll separate out 20 for validation, run a calibration on the 80, and then predict on the 20. And that's fine, but you also need to be aware that if we're going to use this for inline use, then we also have to be careful that we're getting good results from a product that's now running a week after on the calibration that we developed a week earlier. So that's why you need to run validations reasonably continually, depending on the process and how confident you become in the process itself. Once again, I mentioned before that you can detect through mapping that the new samples are no longer fitting to original model. So there is indications that something is not quite right. So, but you still to be very confident, you need to continually do validation samples. Now, also defining our results, we used as well as the RMSECV, we also use R or R squared, which is the coefficient of determination. And this just quantifies how well the predicted versus actual actually fits to a straight line. So, as I mentioned before, R or R squared equal to 1 is perfect, and then R squared drops down. We're not getting as good, not predicting as well. The RPD is very useful in that you should calculate that because it's the standard deviation of the sample set divided by the standard error of cross validation. What that means is that you need your standard error of cross validation to be less than your standard error in your sample set. If it's not greater than 2 or greater than 3 here, as I've indicated, then you've probably just got a random number generator. You're not doing anything at all. So near infrared spectroscopy advantages, again, we'll just cover a few more of these. So there's minimal to no sample preparation. We have deeper sample penetration than mid-NIR, and especially for high moisture product. You can get high scan speeds down less than a second, which is very important for inline use. High resolution, so we can work with down to 0.1 nanometers if required. And it works with a wide range of application, so it works on all organic material, mainly because of the CH, OH and NH molecules, and some inorganic material as well. It can work in 2 modes of operation. We can use quantitative analysis or qualitative results. The advantage of qualitative analysis is a little less time consuming. There's no sample preparation to do. All we're doing is mapping the spectral signature into a different set of coordinates and measuring the variation that we're getting on that mapping. There's no phase constraints. It'll work in a gas, it'll work in a liquid or a solid. Depending on the absorption of the material, you'll either be working in reflectance mode, say for powders, or in transmission mode for liquids. It's non-destructive. There's no contact required with the material. So the inline use can be monitoring your process or your material 24 hours a day, 7 days a week. And it's faster and safer than it doesn't require any chemicals. So often with mid-infrared spectroscopy, you need extra chemicals to mix with the sample or the product before it can be measured on the instrument. So the disadvantages, recapping these. So it's important to measure, like all science or engineering. The sample selection is critical, or important anyway, and it's particularly important to match up the sample selection with the spectral data. There's no point collecting spectra from part of your process line and then taking a completely different sample set to measure the actual constituent value. They have to line up exactly to be workable. It's a black box. It's not easily understand. Sometimes I don't see that so much as a disadvantage. Sometimes it can be an advantage. You don't. I've been working with near-infrared spectroscopy for over 10 years, and whilst I don't particularly can't claim to understand the statistical analysis that goes on behind it, it hasn't shown to be necessary. But it is important to understand the fundamentals so that you have some feeling for what's going on. So model development and maintenance is an ongoing expense. So as I mentioned before, depending on the process, continual validation is critical to make sure your models are predicting accurately. And typically able to measure organic constituents to about the 1% area. And this, for instance, I measured talked about the acid before being less than in fruit, or fruit orange juice being typically less than 1% is more difficult to determine. Although I'd say that this is improving, so there is a lot of research being done to measure components down to levels a lot less than 1%. So I think you'll see that. I'm sure you'll see this improve as time goes on. So a few examples of where it's been used is in beef. It's used for measuring fat, protein, and water content in emulsified meats. And here you can see the wavelength range used and the value of R. So value of R greater than 0.9 is quite good. So online, that's lean beef blended to increase the fat. So a lot of mixture and mixing is done to control the fat level, and that's particularly done for also in milk products. So there's a minimum requirement for fat level, so the closer that the processors can get to running to their minimum, the more economical they are. Intermuscular fat in meat is also can be measured down to 1.2%. Usually with the wavelength range 1100 to 2.5 or 2500 nanometers, with R squared of greater than 0.98, which is an exceptional result. Some things don't work. For instance, tenderness was tried for meat also, but its R squared was 0.65, so it's not really applicable. Needs a lot more work. So there's more examples here of use for beef. Also, adulteration of beef with the lamb, pork, or skim milk powder, wheat flour. That would be a qualitative analysis. So what you would find is that the mapping of the spectral data no longer maps into what you'd expect for pure pork or pure lamb. So you'd get an indication of something's been added. You might not necessarily know exactly what's been added. You just know that something has changed with the product. Microbial spoilage is one big area of research at the moment. Now, a lot of work's been done on that, and it's a fairly new area. I think once this will become very applicable to the food industry once they can crack this nut. Pork, similar with pork, measuring fat, moisture, and protein again. Fat's very good, moisture's good. Actually, all of them. Protein is R squared at 0.97, so very good results. Chicken, I measure the pH, colour, shear force, tough and tender. It's also classification of cooked and raw meat using VIS and NIR. Fecal contamination of chicken skins using visual NIR. Microbial spoilage, I would say that's not necessarily been used in line yet, but it's a lot of research has been done in that area. As I mentioned already, dairy milk is just about every dairy in the world now would have near-infrared spectroscopy used to measure the fat and protein and lactose of the milk, whey protein, fat, processed milk. Dairy, cheese, dry matter, fat, and moisture. Cholesterol, although cholesterol results from memory weren't that good. Butter is also and powdered dairy for measuring water, fat, and protein and lactose. So you can see there's quite a few examples. Margarine's been used in line for quite some time for measuring moisture. Honey can also detect if it's been adulterated with fructose or glucose. If you're promoting it as pure honey, it can easily be measured that it's not. It's easy. Coffee, you can discriminate between normal and decaffeinated. If that's useful or not, I don't know. Cereals, it's probably the cereals are the biggest user and the longest. If I go back 25 years for cereals, measuring protein, moisture in things like wheat and all grains, to the point now where they're actually used in line on harvesters. So initially it was just used as batch processing or batch analysis of grains going to the processing plant. The growers were paid on the amount of protein of their wheat. Now the growers are actually using the instruments in line on the harvesters, and from that they can map the protein level to any point in their property with via GPS. And they can then use that to correlate with fertiliser levels, all sorts of things, irrigation and so forth for different types of crops, to actually better manage the protein or the quality of their product. So used in the paper industry to determine yield of or the kappa number for kraft pulp and black liquor for making paper manufacturing. For in the future. This is what's with the multispectral imaging cameras now. They're really a combination of a near-infrared or a spectrometer and a two-dimensional video camera. So instead of each pixel representing red, green, or blue as a camera typically does, each pixel will have 250 elements or 128 elements or whatever associated with each pixel, and each pixel in that pixel will indicate a wavelength range. So now we've got to, with near-infrared spectroscopy, we collect light through our sample. We're not necessarily looking at the complete surface of the sample or the complete volume of the product. Where the light is diffracted through the material, and then it's measured by our detector. But it's not representative of a visual image. So whereas these hyperspectral cameras will not only give you a picture of the object, but each pixel will tell you what wavelength that's responding to. So that'll be particularly useful for, say for instance, you could map the whole surface of a block of cheese, and you'd be able to determine over the surface of the cheese what the protein level was at each pixel. And that, depending on what the product is, that may or may not be useful. So future analysis is a lot of research been done in fluorescence spectroscopy. It's been used for lab use at the moment. So, and also for microbial and bacterial quantification. that will be a big future development in infrared spectroscopy. So you'll see it in the lab first, and then transferring it to inline use will be quite a challenge, I would think.